What I was talking about? Yeah, a couple of examples of time series so you at least understand what people are trying to do with this. First of all, we as humans are great sources of signals. And we can measure signals from our brains, from our pulse, hearts, even our muscles. We can digitalize it, and a lot of wearable devices and medical devices do it, at least to make our life better, healthier, and make us live. If we consist of sources of the signals, maybe we also can do something that makes signals. And that's mainly our businesses. That's the markets, that's our shops, businesses, whatever. That's our manufacturing things. They should be digitalized, quantized, so we can measure the performance. The same as we measure our ECG, our EEG, the same we need to measure what we do numerically. And if we are signals, if what we do is signals, maybe universe and nature are signals too. And again, we can digitalize it as well. The wind speed, the temperature, the sunspots, a lot of things from the cosmos and the space, we all can treat it as different time series or signals. And two main tasks we are doing machine learning, of course, are classification and prediction. Especially prediction, here you can say regression, if you are from another field. Two main tasks, and I'll try to show typical examples of these tasks, how they were done, let's say, before, and how deep learning deals with them. Maybe you don't see it really well. It might be my fault. But on the left graph, it's typical graph that is really seasonal and goes up with time. It can represent, for example, sales of the air tickets. It goes up with the years, and it's seasonal. This is something that you can forecast even without any mathematics. You can look at the graph. You see, OK, it grows on the long term. It's cyclical on the short term. And you can predict even next year, next 10 years. You need just your brain or something really simple mathematics. You might know about decomposition methods. You might know about methods based on self-correlation, like autoregression models, moving average models. But you can solve it just looking at the plot. Second is an example of ECG time series. That's what I'm working on in this project. It looks like this. And as a cardiologist, I can geometrically, visually see all the parts. I understand that this peak means this phase of the heartbeat. This wave means for this. And I see that some wave is absent. You have atrial fibrillation, for example. I clearly see it by my eyes. My question is now, how do I develop the mathematical models? For the sales, as I said, decomposition, self-correlation, that's what clearly explains the trends. For ECG, yeah, much more difficult. I need to build some models, like mathematical models, algorithms, but still I can code it, I can do it. But why do I need to rely on linear models like correlation? Or why do I need to rely on some really hard-coded patterns if I can rely on approximation properties of simple neural networks that can approximate any ARIMA, any decomposition, because they're simple linear transforms, linear operations. I can highly regularize a perceptron to make it a bit more, not nonlinear, but make it more adaptive to my data. And why should I hard code the geometrical patterns from ECG if I know I have convolutional neural networks, it is designed to find the local patterns? I can learn these patterns from the data instead of hard coding them. OK, but this is easy, visually easy things. OK, next example. On this kind of data, it's already a bit difficult to understand just looking at what is going on. First one is a sample from EEG time series. It shows some brain activity. Well, I think you can't really tell what's going on unless you're a doctor. Second time series is from the accelerometer. Basically, it's 3 axes from your mobile device, from your wristband, and it shows different activities. And I think you can really mistake walking and biking by your eyes. But what characterizes this kind of data if you want to model it mathematically? Someone has an idea? OK. Most often, it's frequency-based approaches. Basically, these signals, they have different frequencies, so you can use Fourier transform and to check if it's what frequencies, high or low, or mix of them, are characterizing every kind of class or kind of activity. But OK, Fourier transform is kind of bad because it doesn't check how it changes over time, because it's just fixed transform. Okay, there are wavelets. You can check how the frequencies are changing over time. So it sounds like perfect. Wavelets, fixed family of functions. And that's what we want to fight in mathematical modeling. That's what we want to fight with AI, machine learning, whatever. We want to come from the fixed models to something that learns by itself. And having in mind that this is what's really determined by the frequencies, this nature of the data, and that I want to see how it evolves over time, I'm again coming to convolutional neural networks. Why? Because to prove you that we're still working on the frequency space, convolution in time domain means multiplication in frequency domain. If I apply convolutional neural network for time series, I still can interpret it as working is a frequency domain. I'm not coming back from the basics, from the roots. I don't want a fixed wavelet family. Okay, I can learn really different kernels of different size and different scales. And actually, it works really good. If you Google recent papers on biosignal analysis or something what's the data that looks like this, maybe from some devices manufactured in time series, you will see convolutional neural network approaches, because that's what works. Okay, there are another kind of data, financial econometric. And a lot of experts, they say that they can predict it or classify it. But actually, if you think a bit, we know that financial time series, they are not really driven by the series itself. For example, I can't say that, I mean, some people believe in this, some people don't, but we can't be sure that from the past correlations, I can predict future correlations. I don't know how to do it. And I can really say that frequency in one part of this time series can determine the frequency in another part of time series. But what's driven the markets? What's driven this kind of data? There are some hidden interactions. There are some things that happen in the real world that affect the prices of some assets. So they're hidden from us, but we still want to model them somehow. So we need to come from this space of time series itself to some hidden state time series. When the state is changing, you want to model how the state affects, for example, the prices in this case. So we are coming to the territory of so-called state space models. They're known for years. And basically, you know, maybe hidden Markov models, at least you heard about it, read about it, something like this. But again, these kind of models are not perfect. And you will not be surprised, reasons are the same. Hidden Markov model, it's Markov. It means no long-term dependencies by definition. And also it's difficult to train, it doesn't really work for high-dimensional data. There are some models from econometrics, like dynamical factor models. Doubtful. Kalman filters are really cool. Okay, I'm not an expert in Kalman filters, I just tried them a couple of times. But when I tried them, I needed a model, mathematical model of a system. And it's not always the case. And I don't really want to build a differential equation by myself. Okay, that's a case for recurrent neural networks. They are designed to have a hidden state. Some of them are designed to have a memory, which supposedly, I'm saying supposedly, learns this kind of transitions. Why I say supposedly? Because just imagine if how actually a lot of people do, a lot of practitioners do, and it works for them, for ECG analysis of 30 seconds of cardiogram, where in each second are 500 points, you want to apply a recurrent neural network. So you want to learn a hidden state that is changing, 500 multiplied by 30 points. How about backpropagation for this? Oh, really nice to learn. No exploding gradients and something like this. So, and there is another problem with this case. And of course, designers of TensorFlow, PyTorch, and libraries, they know about it. So basically, when we use recurrent neural networks for this kind of long data, what comes in the game, what's called truncated implementation. Basically, it does backpropagation just for the last, let's say, 1,000 points, 10,000 points. But what about everything else? So recurrent neural networks from Keras, maybe it's not the best case. And the last works from 2018, also 19, show that another class of models called autoregressive networks, mostly autoregressive convolutional networks, deal with this problem better. Basically, the idea is pretty simple, that we use convolutions that is kind of changing over time. And to keep the context, keep the knowledge of the long-range dependencies, because that's why we want the recurrent network to have the memory, to have the state, we use dilated convolutions, or dilated. Who knows about dilated convolutions? Okay, basically, not many, it can explain pretty simple. We have a convolution of the size 3. It works on the 3 points. I want a convolution of the same size that will work on more points. I can say point 1, okay. Then I skip 1 point. Then again 1 point, skip 1, and again. So it's like a convolution with the holes. It skips some points in between, but it keeps the larger context in the time series. And you can make 2 holes, 3 holes, whenever you want. And this way you kind of emulate the large context idea. And they're easier to train because convolutions still feed forward. They're faster, of course. And works say that they're more accurate. And I can confirm it. OK, talked about state space models. But what we forgot here? Something what we all studied in university, but we don't use it today. Dynamical systems, differential equations. There are still a lot of applications, a lot of models that are designed by some really predefined system, especially in manufacturing, devices that work by defined, well-defined differential equation. OK, there can be some noises, but still differential equation. And actually, a lot of people, what they're doing, to model some situations, we need to fit the differential equation to the data, calibrate it to find the right parameters. And based on this, we do some actions, I don't know, control the heating system on a factory, I don't know, whatever. But we, as AI developers, we are lazy. We don't want to build any equations. We want to stack layers and keras. Oh, that's reality. So the dream is to learn the differential equation by itself. And maybe someone who is following the NIPS conference already knows the solution. Yeah. It was the best paper award from the last conference. Basically, the idea was, OK, the original idea was treating the residual neural network, the deep neural network, as a dynamical process. And they emulated with a differential equation, but they also show how to use it for the continuous process itself. So when you have observations of some dynamical system, and where you don't have all the data points, but you need some kind of to simulate it. Of course, you can use recurrent neural networks or convolutional neural networks. But when you have missing points and different time spaces between the points, it might be really difficult because you're not really sure how to put it in the neural network. So they designed a neural ODE. I'm writing a blog post on this right now. So in the end, I'll ask you to follow me so you can read, have some of the tutorial how to do it. It will be, I think, in 5-7 days. But this is how we can deal with dynamical systems. Well, I forgot something. What types of dynamical processing I might forget? Okay, most probably I don't know about something else, but in my list, that's all from the classical types of data, types of time series of the signals you might work with. At least I haven't encountered any others. But apart of classification and regression, there are other problems that we need to work with. And 3, let's say also most popular of the problems we need to deal with are pattern matching. When I have a database of 100 samples, I need to find which, I have a new sample, I want to do like which one is the closest. And in case of time series, it's not that easy to match the time series. Is it the same or not the same? Anomaly detection, of course, if something different happens over time. And I need to simulate the processes. It's still a needed problem. I still need to understand what will happen under different conditions. Now I'm gonna, after having a sip of water, I'll say how neural networks can help with these 3 problems. And I also want to add that I am saying all of these things not from my head. Everything a part of neural ODEs I try by myself. So I can support you, in the code question, something like this. Neural ODEs, I'll write a blog post and I'll be able to support you too, I hope. Now, these 3 problems. Pattern matching. If you have some kind of vector data from the vector space, and if you believe that Euclidean distance work there, you can just calculate the distance. If the difference is small, they're close to each other. If the distance is high, they're different. That's simple. You can do it in different spaces, not just in the metric spaces. It doesn't matter. But with time series, it's a bit different because they're not the actual objects of the metric spaces. You can't subtract one time series from another one. It makes no sense because it's a process. You can't subtract a process from a process. All right. So I need to, or I need to find some kind of a representation to put my time series into a vector space, or I need to build some procedure to match objects that can move over time. And one of these procedures is already written here. It's called dynamic time warping. Basically, it's a process of optimization to find some kind of the closest path between two time series. And this is what mainly used to, if I want to, for example, apply k-means clustering to time series or k-nearest neighbors approach to classification or regression, you just replace the Euclidean distance with the dynamic time warping distance. That's what people usually do. Yeah. Normal distances don't work. Then dynamic time warping is computationally difficult because it's optimization process running just to compare two objects. And metric learning, you can Google about it, but it's also kind of difficult. What I offer you are two approaches. First one is autoencoder. Who is familiar with the ideas of autoencoding? Okay, a lot of people. Basically, it's a neural network that is learned to, it takes an input, some object of dimension, 100. It squeezes this to dimension, for example, 10, 50, but lower dimension. And from the same lower dimension, tries to output the same initial object. So I want to code my object to some lower space, and I want to code it in such a way so I keep as much information as I can to restore it again. And in this space of the lower dimension, I already can compare the objects because it's a metric space. That's how neural network is designed. Neural network is working not with the processes. It's working with the metric spaces. So it learned the metric space. And I can choose, for example, if I believe that my series are defined by local patterns, I say, OK, I have convolutional encoding decoding. If I think it's state space, I can use recurrent neural network and so on. So it's flexible based on my point of view. And it's fully unsupervised, which is cool too. Sometimes I have already known examples when I have, OK, this time series are similar from, OK, similar in some space, I know what space, because here I say that my space is the best encoding. So I have some kind of bias. I encode the data. It's a nice space, but it's biased space. Maybe I know that I have already a data set and I say, OK, these two time series are similar by some metric, and these two are not similar. In this case, you can try CMS and neural networks. Who heard about this thing? OK, basically, it's a neural network that has two inputs with the shared weights. So if I want to compare if, say, two objects are similar or not similar, I can swap them and doesn't change the result. And I learn with these two networks such a space. So in this space, these objects are or 1 or 0. They're similar or not similar. So I learn the metric function, basically. And this is really powerful tool in a lot of applications. One application you can take into account is biometrical identification, for example. OK, next was what? Anomaly detection. How it's done now? 3 sigma rule. Really good. Amazing. Maybe for more smart professionals, 1-class learning or something like this. Or for example, for the smartest people, fit some mathematical model, and if my prediction from this model diverges from the real observation, it's anomaly. Well, it works, but I want to replace it again with something stupid like a neural network. And again, I can use autoencoders, but already in a bit different way. Now I even actually don't care how well it encodes decodes in some way. I don't really care what this intermediate space is. All what I care about is that I have the data that's supposed to be good. And I want my autoencoder to learn what is good data. So it learns to recover from a good data sample, not anomalous, the same good data with the low error, because that's what it means to recover. I want to replicate the input as close as possible. But if in this network trained just on the good examples, I put something anomalous, something different. If I train it on the cats, and it can restore the cats pretty well, if I input there a human's face, how will be the restoration error? It will be high, because it doesn't know anything about human faces. And this is the anomaly detector. Basically, the first picture is autoencoder. It will output something, and if I compare the output with input, the difference will be too high. I just need to find the threshold. Basically, it's anomaly detector almost for free. But I want anomaly detector for free. I don't want to do anything. I don't want even to find the threshold. And here is where I apply generative networks. How do you think I can do this? I don't know if any of you is familiar with generative adversarial networks, more or less. OK, more or less. I can explain it. Basically, that's the architecture in deep learning that has two neural networks. One network is learned to generate the objects that's supposed to be realistic from the data set I have. And another network is judging if this sample from the first network is, let's say, real or not. And the perfect generation network has been able to fool the network that is telling good or bad. They also called actor-critic model. Of course, it's not the perfect term, but one is actor, one is acting, trying to make something nice, and second is criticizing and telling it's good or bad. So from this actor and critic, what is my anomaly detector for free? Yeah, the critic, the discriminator on this picture, critic is my anomaly detector for free. Because while training to generate and discriminate things, it already learned how to separate good from bad. It already saw so many bad and random samples, so it perfectly knows what is good. For free. It's already a binary classifier. This is, for example, what already works in production in this product. It was just trained on the good card, because when you're measuring your cardiogram, you need to say if you're moving, there are some noises, you just need to cut it off. It was just trained on the good cardiograms, then discriminator put on the mobile phone. That's all. It's done. It works. For free. And the last case is simulation. How do we simulate data today? Basically, for time series, it's stochastic differential equations. We have some model of the data, we have some degrees of freedom, and if I want to simulate some situation, I change volatility or whatever I want to change, simulate it 1,000 times, and see what can happen. And it's pretty good because I change what I want. But again, we are trying to be lazy. We're trying just to learn neural network for what does everything for us. So here we are coming to actually a lot of alternatives. First one is sequence-to-sequence architecture. Who heard something about it? It was applied mainly from natural language processing for translation purpose, because my input sequence is sentence I know in German, output sequence is sentence in English. It was learned to do the translation. In my case, I want to generate realistic future outcomes, for example, of some starting situation. So basically, I take a data set. Again, it's unsupervised way. It's also, you can consider it as some kind of self-supervision. I have my large data set of some time series. I want to have in some 1 hour of something, simulate next hour. I train a model that is just cutting input first hour, output second hour, make this kind of data set, train it, it generates me based on some input. Second and third, again, autoencoders and generative adversarial networks. Generative adversarial networks, GANs, I think you saw something Twitter or YouTube, whatever, you know what it does with the human faces. Some of you maybe know the site, this person doesn't exist. It works pretty well. And if it works this well with faces, high dimensional difficult data, you can imagine how it works with time series. Variational autoencoders are good because in this way, when I have this fixed inside representation, I can manipulate it. So if I encode it, again, I can, later when I'll upload the presentation, I'll add all the links because there are a lot of links for the works, for the blogs and everything. I'll show an example when I was manipulating the cardiogram to make it, for example, more sick or less sick based on the autoencoder. It means that I have my representation knowing about all the properties of the data, so I can simulate different properties from autoencoder. And again, neural ODEs, I'm still working on this, but at least authors claim that it also can generate as variational autoencoders. That's what we have now. And now I'm repeating this slide because I think now we can try to answer the question. Is deep learning the final frontier and the end of signal processing and time series analysis? Who thinks that yes? Oh, so you don't believe what I was talking about for half an hour now? It's all right. Okay, so everyone else is saying no. Okay, who doesn't believe that it's the end? Okay, everyone else? Okay, we are still waiting. Okay, but the final, let's say, asymptotic approximation. But I haven't finished yet. I want to defend because I believe that it's the asymptotically coming to the final because if we're using ARIMA's linear models for years and we actually rely a lot of things on them, and this is much more powerful, and I don't know what can be better. There's linear ALIMA, there's universal approximator neural network. What can be next? Okay, and there are some success stories. Public success stories, let's say, not just what I tried in my startups, because you might not believe this. First two examples are Kaggle winners. Neural networks overcame everything else. Stanford ECG research works better than the cardiologist. That's what we are replicated basically in our project. Uber forecasting, their financial models, their planning is based on neural networks. DeepMind WaveNet, autoregressive model, for audio, for control of manufacturing. And the last thing that I think you also can Google, or I'll add the links, from the EEG. I think you saw that from EEG, they restore what people are thinking, what people see in their heads. From the EEG signal, they restore the pictures. Okay, blurred pictures, okay, not perfect pictures, but they do it. It's just thanks to deep learning. From the raw EEG signal, restoring sound and blurry but images. To me, it's impressive, even taking just these examples. Of course, people who say no or who don't know, you'll tell me that it's not interpretable. It's a black box, and I don't know if I can show it to the client. I can give it to the military applications because I'll shoot someone, and they'll say, deep learning says shoot him. I don't know. Or to the doctor, you can say, I'm not going to use your bracelet. It will say me that I'm not sick, but I'll die. I'm not going to use it. It's deep learning. Or something like this. This example of signal from this device and how one of the simplest approaches to visualize the outputs of the neural network is proving, visualize the inputs of the neural network is proving that it takes into account that it emphasizes only the things that doctor is telling are relevant to tell the analysis. I'm not going to dive into medical details, but it's highlighting what a doctor would look into if saying if this person has or hasn't atrial fibrillation. It's fully interpretable model. You can point it, you can show it to the doctor, you can show it to everyone. We talked to several cardiologists, they confirm it. It's what they would look into. This is waves. If they're present, this person is not sick. In another case, it will highlight other regions. But of course, there are fail stories. And one of the biggest fail stories was 1 or 2 years ago. There was a work showing that group of guys compared the statistical models like ARIMA, exponential smoothing, whatever, with different machine learning models. And they say, look, on our data sets, statistical models work better. Your machine learning does nothing. That was one of the main fail stories, but I really doubt it because if you apply machine learning to a data set that has 50 50 time points and you expect it to work good, well, you can clap yourself and post some nice paper in a journal. I mean, of course, if you have 50 data points, you shouldn't use machine learning. I think if you do some mathematics or engineering, for you it should be clear. Of course, you should find the self-correlation pattern in this similar data. But if you have 500,000 of data points and you're looking for the linear correlation in it, all right. If you like classical models and you can't stop using them, I offer you the hybrid solution that I also had some practical experience with. This is the picture from the Uber work. Basically, that's their model for the forecasting different events. What they do, they train the autoencoder for the, let's say, deep learning representation. Then they have a lot of features on the left from the classical analysis representation, then combine it as the input and use it together. Because say we also want to believe in, Kullback-Leibler score, in entropy, in some house theory features, because we believe it works. It's our features, we believe in them, we want to use them. Why not to combine? But I have for you even better alternative, which Uber guys didn't do, but other guys are doing. If you worked with some things like entropy, the trend fluctuation analysis, basically what's called house theory, you know that there are some combinatorial algorithms that if you want to apply them to long sequences, it's kind of difficult to compute. And it's something not for the real-time use. And you can't use, for example, entropy on a long sequence as an input feature because you'll use much more time just to compute this entropy. What I want to offer you in this case, so your, let's say, prior knowledge, prior assumption is my model should know about entropy. You can use it as the input. But we know that convolutional neural networks are universal approximation functions. What we, alongside with our main loss function for regression, classification, whatever, also learn to predict the entropy. Maybe with some regularization coefficient lambda. Maybe I know, okay, I want it to know a bit about entropy. But I want to bias it a bit towards knowing this feature, this function. This is what's called multitask learning, when alongside with your main objective function, you learn something else. Something was probably a bit relevant. For example, entropy function. For example, alongside with the prediction of the stock price, you predict the future volatility. Or if you believe that the market is moving by some stochastic diffusion equation, you predict the parameters of the calibrated equation. So you make your neural network know about properties of the diffusion equation. That's the idea. And it really works really well. I'll also give you the, I'll give you the link of my tutorial. Basically, with the code, you can replicate it to see that it works on several applications. That's my, let's say, final idea to you. Regularization is not just L1, L2 dropout. Regularization is, first of all, the prior knowledge. Prior knowledge should be not just on the parameters, that my parameters should be bounded by L2 norm. Your parameters can also know about something. And takeaways from this short speech. Time series are everywhere. I know that with all the deep learning hype, we kind of forget about it, but there are a lot of jobs, projects, startups, whatever. We need to measure things, classify things, regression things, and whatever. I try to show you, of course, it's just, let's say, my personal point of view, that to any of the classical approaches to modeling, there are the neural alternatives. That, again, from my point of view, are better. Mostly because of the linearity and some kind of simplicity and boundness of the classical models. Next, if you have any adequate size problem with time series, I suggest you to start with convolutional neural networks. Or in case of hidden state space, autoregressive convolutional neural networks. We can discuss about it, of course. I also really suggest you to try unsupervised learning for different embeddings. For clustering, for anomaly detection, even for the simulation of the data. It really works. Yeah, simulation already said. And the last thing, it's really nice, at least now, because the neural architectures now, let's say, not perfect, we all know this. So if you regularize them with some nice features that you already know are useful, it's really a great idea and it works in practice. And if you want to work with me or something like this, ask me questions. If you want to criticize me, if you want to say in my blog that I don't know nothing, here's where you can say it. Thank you very much for your attention.
Thank you for the talk. I liked it a lot.
Thank you.
About 5 minutes ago, I was about to say that I don't like it, but actually I liked your last slides.
Mm-hmm.
So, and actually this is my point that I wanted to ask you. So you work with ECG data. So I'm not sure how to say it, but let's say this is the kind of data where Y becomes very important. So you highlighted these points there in the on this slide. But then, of course, you need to be able to say, what about those points that you highlighted?
Yeah.
And this is actually the other aspect that I didn't like so much when you were saying always, you get it for free, it's very easy to do. I think there's a lot of value of doing things the hard way because you learn a lot why things work. I do tend to think of deep learning as brute forcing algorithms. So I don't want to make it too broad, so what kind of interpretational features or ideas have you tried in your particular project? Thank you.
Basically, for determining atrial fibrillation, main features are the disorder of the rhythm, so the distance between the heartbeats is changing all the time or the beats are skipping, and this P wave is absent and becomes kind of very noisy. That's basically two main features of atrial fibrillation we want to detect. As you can see, here is the healthy person when just the present P waves are detected. You might not like my answer, but we have a neural network model that annotates all the waves. Basically, it says it's R peak, it's P wave, T wave, another wave. So basically, I have the highlight. Another network is saying it's my P wave. I say P wave in these moments of time are present. That's the explanation. Or the otherwise, P wave in these times are absent, check it. That's it.
Other questions? We have 5 minutes before the end of the call. Okay.
Thank you for the talk. It was very interesting. I have a question about hybrid methods. When you talk about add prior...
Sorry, what methods?
Hybrid methods, at the end, you talk about adding prior knowledge. Mm-hmm. And do you mean something like Bayesian deep networks or something? Okay.
Okay, I know what you mean. For example, mostly when we say prior knowledge, it means that on the parameters of the model, we put some prior knowledge. For example, I can say in Bayesian framework that my ABC are Poisson distributions with this kind of limits, or you know what I mean. Or for example, in case of regularization of deep networks, I say my weights should be regularized with the L2 norm of the weights in this layer, or all the weights. And we call it prior knowledge. I know that the term I use here is a bit wrong, but it's like my interpretation, my metaphor. My, let's say, prior knowledge about the model is that the model knows, for example, about the entropy. So how do I make my model know about entropy? It should be able to predict the entropy from the input data. So it needs to know now two things, the main objective and entropy. In case of neural networks, it's easy to do. It just has to have two outputs. And to make it regularized, not to emphasize on the entropy instead of the main loss function, I put some regularization parameter on the loss with the entropy. This kind of framework. The same as you put your lambda next to the L2 regularization, now you put your lambda next to the entropy mean squared error. That's what I mean. It's, you know.
I'm not sure if I understood correctly. At some point, you said for simulation that with an hour of data, you can train your neural networks to produce the next hour of data. That confuses me. I would assume that for training you need a long time series so that the neural networks learns all the possibilities. Probably, unless your data is extremely fast and then you saw everything, that looks a bit extreme.
I agree. The first case here is maybe not the best example. It's not always suitable, but it's good in the cases when you, for example, you sometimes need to simulate based on the something. You not always simulate, random stuff. You want to say, I want to understand what will happen if I have this primary situation. And this primary situation can be some sequence of events. And this is, natural situation from sequence to sequence. And I understand that in most of cases, it's not the case. So that's why I talked a bit more about autoencoders and GANs. I understand your concern. I understand it's suitable only when you have it in mind. If you have, based on this 5 seconds, I want to predict next 5 seconds because that's what you need. And that's where it can work. It's really kind of small case.
Okay, I think we have time just for one last question. Sorry.
Again, thanks for your talk. And thinking about your slide with all the successful examples of company that applied deep learning. So when I see this company, I think that they have really big data.
Yep.
Okay, so my question is, sometimes I have to build models for time series forecasting, but I don't have big data. Like I have daily data, and I am lucky if my company provides me like 10 years of daily data, maybe 5. So let's say 1,000, 2,000 samples. Mm-hmm. Isn't it a risky move to apply a deep learning algorithm for overfitting issues? So I'm going to stick to classical and simpler algorithms.
I agree that if you, let's say, don't really have large data sets, you must probably need to stick to the basic models because in the small, let's say, roughly speaking, in the small world, these models are proven to be good because they're modeled for this small world. But for the large world, that's why basically deep learning works today, because for the large world, it's difficult to find this kind of perfect model. So of course, all this stuff is for the huge data sets. What I might suggest to try is highly regularized but simple neural architecture. So basically, the idea you might have in mind, let's say, for example, your ARIMA works well, you tune it with different parameters, but you might suggest some small non-linearities in some moments, and you know that over highly regularized neural network can catch them. So that's what you might try.
Okay, I think we finished. Thank you, Alex.
Thank you.
And